Alright, good morning. So sorry I'm a little bit late, stuck in traffic. So let's continue on the pole placement. Okay. Hopefully we can finish this pole placement today. So just a quick review on the pole placement here. Okay. So this is the state equation of the system. And what we want is, your objective is we design a feedback system, and the feedback controller, we're dealing with a single input, single input, single output, so we'll just get rid of the vector sign. So this feedback is a negative feedback, and the feedback is based on the state variable x of k, right? So essentially, this is the simple controller you're designing here, and the key here is what we call the gain matrix, or matrix gain. Okay, so this is basically what you want to design in here. Okay, so this is a design parameter, okay, or control gains, right? So overall, the whole system, if in terms of a diagram, so this is your x of k at here, and this is your u of k. Okay. So now what we need is we are feeding this back, okay, and give it to a negative here. Okay. There we go. Right. So that's giving you a feedback system here. Right. Okay. There's zero reference set here. Basically, it's a zero. Okay. So what we call this kind of system here, what we call it the regulator. Okay. We call it regulator. So why is it regulator? Because if we plug this u of k equal to negative kx of k back into this state equation, right? So very simply, you can see now this is basically becomes, okay, it becomes this, right? So with feedback, your state equation becomes this. Right? The state equation becomes this. So the state equation, this is the key here, right? This is the key. And this part here, we call that the system matrix. So originally, G is a system matrix here. Right now, it's with the feedback, this one is. So the eigenvalue of this one, so the eigenvalue of this basically determines the response or the characteristics of the system, right? So the location of the eigenvalue of this guy here. And G and H are known in the system matrix, so we can't change that. So the only manipulable parameter that we can work on is this K edit here, right? So basically, right, we can choose K, okay, to have a desired, okay, eigenvalue. Okay, to desired eigenvalues. So that's the purpose of this so-called pole placement. So you choose a proper K, so you place the desired pole at somewhere that you want. Okay, that's pole placement. All right. Yeah. Now, in terms of the general approach, here, let's say we do this, right? Let's say we choose z equal to lambda 1, lambda 2, okay, up to lambda n as our desired poles. Okay. Okay. Suppose this is a desired poles here. Okay, this is a desired pole, and we learned that in linear algebra, when you're talking about eigenvalue of a certain matrix. So basically, what we're saying is it's this. If you look at this one here, eigenvalue of that, okay, is basically the solution, okay, the solution of this determinant at here, right? So this equal to 0. In other words, solution of this gives eigenvalue. Okay, yeah, solution of this gives eigenvalue, and solution of this one here, basically the determinant of this matrix essentially is a polynomial out here, right? Yeah, essentially a polynomial. So what we want is, right, looking at the relationship here, okay, so this is your Zi minus G minus HK at here, okay. So what we want is, we want this guy to have poles or to have eigenvalues at where? At lambda 1, lambda 2 to lambda n. Okay? Yeah, that's what we want. Okay. So basically, we want this one to have the same poles here, which means we want this guy to be the same as this. Okay, so that's basically what this means by pole placement here, right? Yeah. Very good. Yeah. So let's say we call this is a polynomial. Okay, it's a polynomial or a function of z. Okay, so we can give a name at here. Okay. Now, remember what happens right here, okay? This is all known here. So this is basically lambda 1 to lambda n is a known one, is what you're given, right? And this side here, there are unknown parameters, which is what? Which is basically the component in the K matrix, right? Yeah. So if you remember, I mentioned the K here. K is a gain matrix. X is n by 1, so K at here is the 1 by n, right? So there are n components in this vector K at here. Okay, so there are n numbers. So basically, K maybe is K1, K2, and 1 by n, right? So K1, K2, and up to Kn, like this, right? Okay. Yeah. So then, when you plug this K into here, so this side here, right, is also polynomial, but that polynomial contains the K1 up to Kn. Make sense, right? And then you compare this guy with this side here to solve for the K1 to Kn, basically. All right? Yeah, that's pole placement. So let's take an example, simple example here, and then to illustrate this idea of pole placement here. Okay? Yeah. But before we move on, let me state this theorem here. Okay? State this theorem. The necessary and sufficient condition. Okay, the necessary and sufficient condition for arbitrary pole placement is that the system is controllable. Okay, so in the previous lecture we learned controllability and observability, right? So the controllability basically saying is if the system is controllable, then you can find some piecewise control input to bring your initial state to certain value of a final state, right, within a limited number of sampling period. That's controllability. So now, if you wanted to do a pole placement design, okay, then the necessary sufficient condition for arbitrary pole placement is that system is complete state controllable, which basically means if the system is controllable, you can place the poles, okay, anywhere you want, course, you don't want to place the unstable post, but that's basically the meaning of this, right? Yeah. Okay, so let's take an example right here. Okay. Yeah. And I'm going to use a so-called double integrator for example right here. So let's say you have a system g of s equal to 1 over s squared. So this is a double integrator. Okay. And double integrator is a fairly common, it's simple, but it's actually a fairly common system. For example, if you have a rod, okay, and it's subjected to certain rotation with a certain torque applied to it, okay, so that torque equal to j theta double dot. Okay, so j is the moment inertia, okay, multiplied by this theta double dot. Okay, I suppose it's a pretty short rod here. So if you take Laplace transform of both sides right here, then input is torque and output is theta. Okay, so then what do we have here? We have input is torque. So theta of s over t of s equal to what? 1 over gs squared, right? 1 over gs squared. So that's a double integrator. Okay? Yeah. So double integrator is a fairly common system. So now let's design basically a controller, okay, for this system here. We're going to design a discrete controller, of course. So first step is I'm going to discretize this model right here. Okay? To discretize this model, the first step is we need to rewrite this one here into a continuous, okay, continuous state equation, state space equation. Okay. Now there are different ways of writing this state space equation here. I think I'll skip a few steps. You can take a look at the. I'll give you appendix for this lecture here. Okay. But maybe I'll write a few things in here. Okay. So let's say I'll use y of s over u of s equal to 1 over s squared. Let's say this is the input-output transfer function in here. Now, if you remember the way we write the continuous state space equation, what we do is you can do this, right? You can do y basically double dot t equal to u of t at here. Then you can let x of t equal to, sorry, x1 of t equal to y of t, x2 of t equal to y dot, okay, yeah. Then, which means x1 dot equal to x2t, and x2 dot, okay, equal to y double dot, and which equal to u of t, right? Okay, that's simple like this. Okay, so then the state equation will be, okay, x dot equal to, what's the coefficient for x1? 0. Coefficient for x2 is 1. Coefficient for x1, x2 are both 0 here, and the x of t. Plus, there's only one u at here, so 0, 1 at here, and u of t. Okay, so this is your continuous, okay, state space model. Okay, now we discretize this one here, and this is your matrix. Let's say A here and B here. So you discretize that according to the formula we derived in previous lectures, right? Yeah. So with the discretization, okay, we end up with ourselves. Okay. So then, all right, now here discretize. When you discretize, we discretize that basically using zero order equivalent, right? So after discretization, what we need is we need the discrete model. Okay, we need this one in here. Okay. And the G at here, of course, and G and H are basically based on this A and B discretization. Okay. The formula, if you remember, okay, that G is e to the power AT, and and h 0 to t ea lambda d lambda by b. Okay, so that's g and h. Okay, so overall the g end up with this 1 t 0 1 at here, and h, okay, end up with t squared over t here and t and here. Okay. Okay. So that's discretized model. Now the next step is we're going to design a digital controller based on this discretized model. Okay, see the process here, right? Yeah. So we're not designing a continuous controller and then discretize the continuous controller. Basically, we design a digital controller based on the discretized model. Okay. So the model of course the controller we're designing here is a pole placement. Okay. So what we do is we design a u equal to negative k xk here. Okay. And we know that k is a vector, so if we expand it out, basically it's negative k1 x1 of k minus k2 x2 of k. Okay. Yeah. Okay. So give this u back to the system at here, and what we have now is x of k plus 1, right, equal to g minus hk and x of k. Okay. So we give it back to this original system. All right. So let's. I have the g, I have the b, I have the h, I have the k at here. So this matrix at here, if you write it out, okay, it will be so this is the matrix of g minus hk at here. Okay. Okay. So right now I'm keeping the sampling time t at here, so you actually can have a general basic expression for the k1 and the k2 in terms of the sampling time value. Okay. Is that okay? Yeah. So the characteristic equation, okay, of this, basically the system in here, is zi minus this g minus hk in here. Okay. Characteristic equation is this, and what's this matrix? This is the matrix in here. So you plug this one over here, right? Plug it here. Okay. And Zi is basically a unity matrix, and I is a unity matrix 2 by 2 multiplied by a variable z. Yeah. So once you get this one here, and then you take determinant, so it's going to be a 2 by 2 matrix, right? So that's not going to be too bad. So if you take the determinant, you get a polynomial, which is this one here. Okay, so then you get this polynomial here. Okay, so this is a polynomial based on the feedback. Okay, based on the feedback, but we haven't given a value of a k1 and a k2 yet. Okay. All right. So what do we do with this one here is, now what you do is, what's the desired, basically, what is the desired, okay, characteristic equation? Okay. Desire meaning you pick two desired poles for this system, right? So let's say I pick lambda 1 and lambda 2. Okay, pick lambda 1 and lambda 2 as desired poles. Okay. If you pick lambda 1 and lambda desired poles, and then the desired characteristic equation is z minus lambda 1 and z minus lambda 2 equal to 0. Okay? Yeah. So if you expand this one here, so that will be z squared minus lambda 1 plus lambda 2z plus lambda 1 lambda 2 equal to 0, right? Okay. Yeah. So the desired characteristic equation basically is this, right? This is your desired, and that's based on your desired pole, right? Yeah. And suppose that let's say I simplify the situation here. If I see the desired one is P1z plus P2 equal to 0. Okay, so basically this is a coefficient for the z, this is a coefficient for constant here, right? Yeah. So if I give a desired characteristic equation as this, P1 and P2, right? That's your desired here. This is your desired, and this is your actual, right? This is actual. So what do? We want the actual one to be the same as desired, which means we want this coefficient to be the same as P1, this coefficient to be same as P2, right? Yeah. So that gives us two equations. So K1 t squared over 2 plus K2 t minus 2 equal to P1. And K1 t squared over 2 minus K2 t plus 1 equal to P2. So two equations and two unknowns. So then you can solve the K1 and the K2 in terms of a P1 and a P2. And P1, P2 ultimately come from the poles, right? Desired poles, lambda 1, lambda 2. Okay? Yeah. So once you solve that, okay, and we end up with K1 equal to 1 over t squared, 1 plus P1 plus P2. And K2 is 1 over 2t, 3 plus P1 minus P2. Okay, so that's the solution. So given your desired pole location, you can pick your gain K1 and K2 as using these expressions here. Okay, that's the second order for a double integrator. Is that clear? Yeah? Yeah, so it's not too bad. Okay, so now let's take a look at another example right here, okay? Take a look at an example. In this particular case, okay, this is kind of general here, but the process of picking a desired pose, lambda 1 and lambda 2, was not involved. Basically, this question didn't really tell us. So based on what criteria do you pick this desired lambda 1 and lambda 2, right? Yeah. So you do have a certain criteria, you do have a certain kind of guidelines, okay? Or sometimes we call that the user specifications right here, right? So let's take a look at another example right here, okay? So this time the plant is slightly complicated. It's a second order. Okay. So 10 over this. Now I want you to practice this, okay? I want you to basically, we're going to follow a similar process. You write this one, okay, into the continuous state space model. Okay? Write this into continuous space model. So if you write into continuous space model, it would be this one here. You should try hand conversion first, okay? And then you can use, if you want, you can use a MATLAB to do that for you too. Okay? Yeah. So but you probably will see that the MATLAB will give you slight different results from your hand calculation. So how do you get this one here? Just follow the process as I did in the first example. Just let x of t equal to y of t, x1 equal to y of t, x2, x1 dot equal to y of t, x2 dot equal to y dot, right? You know, that kind of process, right? Okay, so now let's choose capital T, the sampling time at 0.1 seconds. Okay. Then we discretize this one at here. And once we discretize that, okay, we end up with 0.0952 at here. I guess this doesn't have to be that accurate. Okay, so end up with this discrete model here. Okay, discrete model. So this is the discrete model describing the plant. Okay, yeah, the plant. And now we design ourselves a pole placement controller. Okay, we design a pole placement controller. Okay, so let's design a pole placement controller here. Yeah. Okay. Yeah. So let's say, for example, the experiment setup here. Okay, so actually we're going to probably spend sometime in the near future. You go there, you wanted to design a pole placement controller, and so that's the model over here. Okay. The model gives you a position here and velocity. Okay, yeah. So let's say this is basically x1 of k and this is x2 of k, right? Yeah. And input is u at here. So you have this guy here, right? You have this one here. So what are we designing? We're designing a pole placement controller. So what do? We basically insert a gain matrix at here, right? A gain matrix, the k. Okay. So these two, these two, usually you can combine them into one block, one line over here. Okay. So these two feedback over here. Okay. Then see, that's a simple, basically, pole placement controller here. Yeah. So when you design that, you can see that actually it takes you less than 10 seconds to design this thing here, right? Yeah, 10 seconds. So how do you do the K? You double click on it, and there's a interface pop up. Basically, you insert a value of a K over here, right? There's a value of a K. Okay. So let's say initially you didn't do any calculation, and you just say, let's try it out, right? Let's try and errors. Basically, let's see what happens here, right? Yeah. So then, very simply, you say, okay, I'm gonna set this K2 equal to 0. I'm gonna set the K1 equal to 1. Okay? Yeah, or 2, doesn't matter. Yeah. And of course, if you have a feedback here, in this case, when you set it, you should set a negative feedback here, right? But in terms of this expression here, you can just set this one as 1 and here. Okay? Yeah. As a matter of fact, you can take a guess here. So what's the effect of the 1 and the 2 and the 3 and the 4 and 5 when you increase this number here? So this is a regulator here, right? This is a regulator. So regulator meaning that I don't have any reference input to here. So basically, it's going to regulate whatever initial value back to 0. Okay, the control effect of this kind of pole placement regulator here. So if this is the motor here, if you don't touch it, there's no movement here, right? And it's actually nothing moves, nothing here. So if you design a regulator, so what happens is you can twist that motor a little bit, give it as an initial disturbance, and let it go, right? So if there's control in effect, then the control, you'll see that it basically will bring back to original position, 0, right? That's basically the how the regulator works. That makes sense? Okay. So then, back to 0, basically, if this initial x1 of k is 0, then you twist it, you give a certain degrees, it'll go back to 0, right? Yeah, actually it will approach to 0. So the question here is, let's see, think about this one here. If you increase the number, the value at here, 1 to 2 to 3, what would you expect?
It's gonna get bigger.
Hmm?
It's gonna get bigger.
What's not get bigger? You know, so just think the common sense of control, right? Yeah. What does a control do? Actually, when you do PID control, right? What does the P do? P is a proportional gain. When you increase the proportional gain, what happened to the response? Do you have a slower response or do you have a faster response?
Faster.
You have a faster response, right? So if you increase the gain at here, you're expecting what? A faster response. Faster response in this particular case means what? The x1 of k will exactly go back to 0 faster. Okay? Yeah. So next time, remember what I said here. Next time we'll look at this simple effect here. Okay? Yeah. So let's say we set k2 equal to 0 and k1 equal to 1. Okay? Yeah. Then once you plug the u back to this system at here, then basically the g minus hk, the z minus this, right, will give us a polynomial, and we'll figure out that polynomial. In this case, okay, it's this. Okay, it's this. So this is kind of arbitrary here. So we don't even know what pose that we placed, where we placed here, right? Because we just basically pick two values, k1, k2. But we know that once you pick a k1, k2, you are replacing the original pose, or you are placing the pose at a new location in here. So where's the new location of the pose? It's the solution of this characteristic equation of the closed loop, right? Yeah. So here's the second order one. If you solve this one here, you'll see that the solution of this one is, okay, it's a complex conjugate solution in here. Okay, it's not two real numbers, two complex roots. For complex roots, for a plus jb, okay, you can always express a plus jb as rej theta. Okay, rej theta. Or sometimes we say just r angle theta, right? Yeah. So in this particular case, okay, our two complex poles give us this one here. So basically means with the selection of k1 is 1, k2 is 0, you placed the pole okay, at 0.95, which is r, and theta is this, 0.09 radians. Okay? Yeah. Was this okay, the complex thing here? So basically, when you have when you're in complex plane, and this is the real axis, this is imaginary axis, and this is a plus jb, right? A plus jb, and this is a theta here, and this is r here. Okay, so r is the magnitude, theta is the so-called argument. Right. Yeah. Okay, so that's where you place the pole. I mean, if you wanted to rewrite it back into regular a plus jb format, you're gonna just have to use what? The Euler's formula. So this is basically 0.954 cos, yeah, this degree, this reading plus minus j sine of this. Okay, yeah. Okay, so basically it's a complex and you will see that, okay, R at here, which is the magnitude of this, apparently R is what? It's less than 1, right? R is less than 1, okay? And theta 0.09 readings, it's, I don't know, it's multiplied by 557. How much? Yeah, well, you'll figure it out. So, so basically, this the two poles that you place is within the unit circle, right? Yeah, and it's pretty close to the boundary, but it's within the unit circle. So you do have a stable response with the selection of k1 is 1 and k2 equal to 0. Okay, yeah. But that's kind of a a blindfolded things here. We don't even know where we're placing the pole. But usually the other way around it, you wanted to select the pole to pick this k1 and the k2. Okay, yeah. So now here's a simple here. We're going to come back to this later again, but for now, let me kind of give you a preliminary sort of ideas of how do you do this one here. Okay, yeah. We usually do that. We do this. So basically the question is, I should maybe think about this one here. So let's say this is your Z plane here. Okay, this is your Z plane. So pole place means you're picking poles within this unit circle here, right? Within unit circle. So you may want to pick your poles over here. You may want to pick this here, or you may want to pick this one here. Who knows, right? Yeah. Now, where do we pick, right? Should I pick over here, or should I pick here, should I pick here, right? There is a reason in it here, basically. So when you're saying you pick here, you actually know that when I pick a pose at here, I actually know or I actually expect what kind of response gonna be. You know what I'm saying? Yeah? So you learn in control system, in continuous system. When you learn in continuous system here, and what do we have? In continuous system here, you have S minus S1, S minus S2, right? This is the pose of this polynomial here, right? This is posted here. So the location of S1, S2, maybe it's on the real axis, and maybe it's over here, okay? Like this. Or maybe it's on the imaginary axis, okay? Yeah. But guess what? I think you know that. What's the effect of the pole location in here and compared to here? When you have a pole at here or when you have a pole here, what's the effect?
It's more stable.
Which one is more stable? The one is more. When you say more stable, is actually in terms of response, the response corresponding to this pole. It's actually exponentially decay much faster than this guy here. Okay, right? When you have a pole at this location here, so what would you expect to respond? They expect the response going to be some kind of oscillatory, right, response. And the further it to this side here, the oscillation will die down quickly, right? So what I'm saying is, you in a continuous system, of course we're assuming here, you learn to continue, you know that for a certain location of poles, I expect kind of a response that we're going to have, right? Based on the location of the poles here. So here's a similar stuff too, and which is what we're going to talk about next lecture. If I pick a pole's location in the Z plane here, I also can expect what kind of response I'm going to get. Okay? Yeah. So what's the relationship here? There is a relationship, okay? And that relationship, it's connected by this Z equal to e to the power of st. Okay? Do you remember in the previous lecture, how do we convert the S to a Z block? So what do? We get the start of S first, right? So what do we do with S? And then again, we replace the S with 1 over T ln Z, which is basically this guy here, right? So this guy. So that's called a pole matching. So if you have a pole in the S plane at here, and what will be the corresponding Z plane pole? It's connected by this equation at here. Okay, it's connected by this equation, right? So let me deviate this a little bit here. Okay, deviate this a little bit. And let's talk about second order. Okay, let's talk about second order continuous transfer function first. Okay. So I'll tell you why we talk about this one here. So let's say if I have a second order continuous transfer function, and this is kind of the standard second order transfer function at here. Okay, yeah, this is kind of standard one here. This is standard, basically meaning it represents many systems, such as a mass prime number system, RLC circuit. Okay, it's a second order system. And over here, the zeta here is called the damping ratio. Omega here is called natural frequency. Okay, yeah. So for a mechanical student taking vibration, this should be pretty familiar to you. Okay, yeah. And then, why this is important, basically, a lot of systems can be simplified into a second order system. So some system maybe is higher order, maybe it's a third order, maybe it's a fourth order here, right? Yeah. But you can see that in a lot of system here, you can partition that system into a second order multiply. If a third order, you can partition that into a second order multiplied by a first order, right? Yeah. Or if a fourth order, you can two second order system multiplied together. So second order system is a very fundamental system to study here, right? Yeah, or particularly the responsive second order system. So the responsive second order system is given by the pose location. Okay. The pose is the solution of this denominator here. The solution of this one here is negative zeta omega n plus minus j omega n 1 minus zeta square. Okay. Suppose that we have a complex conjugate case study here. Okay. Complex conjugate. Yeah. So here is a continuous system. Okay, this is a continuous system. Now, if we discretize this continuous system, okay, and we will see that, or basically, if you sample this discrete system here using an impulse sampler, you will see that as we learned, okay, the corresponding poles will be matched, okay, with this expression right here. So what is this S? The S is this guy here. So this is basically e to the power of this whole chunk multiplied by t, right? Multiplied by t. Okay? Yeah. Is that good? Yeah. And if this is basically like a plus jb, right? It's basically like a plus jb. And e to the power of st is like e to the power of at plus jbt, like this here. Okay? Yeah. Now, e to the power of something plus another, it's equal to this, right? Is equal to this. Okay. So what is a is that quantity there. So e to the power of negative omega n t. Second one is e j, okay, omega n root of this capital T. Okay, is this. So what is the if you look at this one here, this guy here is a real, right? This is a real part. This is a real number, and it's positive. Okay, it's positive. And second one here, this one here, e to the power of j something. Okay, e to the power of j something. That's basically a theta, right? E to the power of j theta. Okay, can you see that? Yeah. So this is essentially in the formality of r angle theta, that the one that we were talking about there, right? So what's r? R is this, right? This is r. And what's theta? And this is our theta here. Okay, this is your theta. Okay. So in other words, the continuous system pole, okay, is mapped into the z plane at the location of r angle theta at here. Okay, angle theta. Yeah, I should have missed the positive and negative, right? Positive and negative. Okay. Yeah. So this is r, this is theta. Now, what's the relationship between this r theta and the zeta omega n? If you look at this pole location, this is a pole related to the zeta omega n here, right? Zeta omega n. And this is the pole r and the theta. So many times here's the kind of the connection here. You wanted to pick a z plane pose, okay? So then, where do you pick this z plane pose? You actually, first thing you think of is what should I pick in terms of s plane pose? Okay, maybe I should pick the s plane pose at here. Then with the s plane pose at here, you can convert that to the z plane pose like this in this equation with this equation at here. Okay, and if you know how the system behaves according to the s plane pose, and that basically the corresponding z plane pose will behave the same manner as this continuous point s pose. Okay, yeah. So what we need is the relationship between zeta omega n and r theta here, and actually quite easy because we have r equal to this. We have theta equal to that. Okay. So two equations, two unknowns. So we can solve. So we can solve this in terms of this this relationship. Okay. So this is your zeta, this is your omega n here. So giving r and theta, here's the zeta, here's omega n. Okay? Here's omega n, like this. Based on this relation, based on this connection here. Okay, so you can actually try to just take a line of both sides and then square each up, and then you'll figure this out. Okay? Yeah, it's not bad. Okay, so keep in mind here, we're going to make use of this relationship here, okay? We're going to keep this relationship here. And then the second point here is, when you design a continuous controller, so many times the user will give you certain specification. So for example, the user will say, I want you to design a control system such that the time constant is certain values, or such that the rise time is a certain value. Was that right? Yeah. Or the overshoot is within certain percentage. Right? So those are user specification. So for example, if we're talking about time constant, the time constant for second order system here, okay, for this kind of second order system, so we don't have to redesign anymore. Time constant, we call that tau. For the second order one here is 1 over zeta omega n. Okay, so this is your time constant for this continuous system. Okay, so now we have the zeta omega n at here in terms of r and theta. So in discrete equation, what's the time constant now? Just multiply these two together. You get negative t over this. Oh, sorry, I missed a negative here. It's negative. Okay, yeah. Okay, so negative t over ln r at here. So the time constant in terms of continuous one is this. In terms of the discrete one is negative t over ln r. All right, yeah. Okay, good. So now I think I'm ready to go back to the original question here. Okay, go back to the original question. So let's go back to the original question here, okay? And I have this Z12 equal to this. So let me write it down here. So Z1 and 2 equal to 0.94954, angle positive negative 0.09 at here. Okay. So this is the pose with the choice of K1 equal to 0, K2 equal to 1. And this is R, the resulted R, this is resulted theta. Alright? Yeah. So the next question is, based on this R and theta at here. So you know what, maybe I should just draw this just initially draw here. So if you have this pole location here, what we expect? You probably will see a response like this. Okay, so you probably will see a response like this, and that's essentially, you know, like this kind of response, right? Like this kind of oscillation. Okay, there's oscillation here. Okay, but it go back to 0. Okay. So then the question here is, you look at this zeta omega, and then if given the R and theta, what would be the damping ratio zeta? What would be the natural frequency omega n corresponding to a second order continuous system, right? Yeah. So we can plug this R and theta back into this zeta omega n right here to calculate the corresponding damping ratio and omega n, okay, damping constant. So zeta equal to that guy over there. So that can be calculated, which is 0.646. Okay, so that zeta can be calculated with this. And instead of calculating the omega n, I can also calculate the time constant. Okay, I can also calculate time constant. Okay. So the time constant, the calculation will be 2.12 seconds. Okay. So now the next question is, let's say suppose that you are okay with this guy. Okay, so you say, okay, I think this is okay, right? But the time constant 2.12 seconds, so you're saying, okay, it's a little bit too slow. And what we need is, let's say we want tau desired is 1 second. Okay, so we want tau desired 1 second. But we're going to keep this zeta. Okay. Then, how do we change our K1 and K2 to reach or to obtain the desired time constant? You see the point here, right? Yeah, so this is basically the next part here. Alright? Yeah. Okay, how to change K1 and K2. Okay. Okay, so if this is your desired time constant, 1 second here, how do we pick? So basically the question is, how do we pick a K1, K2 again? K1, K2 should be picked based on what? Based on the desired pose, right? Desired pose meaning there is a desired R and a theta. So if you can figure out the desired R and theta based on this time constant, the new time constant and zeta here, then we'll be able to calculate the K1 and the K2. Okay? Yeah. Is that okay? Yeah. So let's try to update this R and theta here based on this new time constant, right? So what's the new time constant formula? This is tau equal to negative t over R here, right? So basically, what you have here is tau d equal to 1 second equal to what? Negative that t over ln R here, right? Ln R. So capital T is given, which is 0.1. And then time constant is 1 second, right? Time constant 1 second. So which means your ln R equal to negative t over tau d, right? Tau d here. So you can solve for the r now. So the r is negative and not negative and positive. Okay, 905. Okay, so r is different now. It's just slightly smaller now, right? Yeah. So think about, does that make sense on that, right? See, your original r is 0.954, which is closer unit circle. Right now, the r is closer to where now? To the origin now, right? So the closer to the origin, the faster the response is going to be, right? Yeah. So if this is r now, okay, and let's see, what will be the theta value, right? What will be the theta? So theta can be solved out of here. See, you have the r here, you have the zeta here, then you can solve for what? The theta here. Okay, you can solve for the theta. And what's the zeta? Zeta is the same value as we kept, 0.46. Okay, so you might pick a different zeta. Maybe 0.46 is a little bit too small. Actually, what's the effect of zeta in terms of continuous system? The smaller zeta it is, what you would have more what? Oscillations, right? Yeah. So this is a damping, right? So basically smaller damping. So sometimes you may want a 0.6 or 0.7 to have a better or less oscillation here. But let's say for this one here, we'll just keep there. So the theta, okay, in terms of that equation, okay, basically in terms of this equation here, right? In terms of this equation, okay, solve for theta based on zeta and r, it's this. So you solve for theta, that updation give us 11.04. I'm sorry, not this guy here. So that give us a theta equal to 11.04 degree. Okay. Approximately 0.193 readings. Okay, so now you have a new r and a theta. With the new r and a theta, which means desired pole is lambda 1 and 2, which is 0.905 angle, positive and negative, 11.4 degree. Okay, so this is your desired poles. Okay. And if you calculate this whole thing out, which is 0.888 plus minus J.173. So that's your desired pose. Once you have the desired pose now, we're ready to calculate the K1 and the K2. And K1 and K2 are calculated based on the desired polynomial. So desired polynomial, or desired characteristic equation, is what? Is z minus lambda 1, z minus lambda 2. Okay? Yeah. So what do? We plug the lambda 1 here, lambda 2 here. Right? Yeah, don't forget the negative minus something, positive, negative things. Okay? So we end up with ourselves z squared minus 1.776z plus this. Okay, so that's your desired characteristic equation now. And then once you have desired characteristic equation, and we'll be able to basically go back to our original one here. Where is it? So it's right here, right? So basically go back to this guy here, right? So plug K1, K2 into here, get the actual polynomial, compare coefficients, and solve for K1 and K2. Was that okay? Okay. So I think I'm going to skip that part there. So then you can solve for K1 and the K2. Okay. Solve for K1 and K2. Yeah. So you'll solve that in terms of that K1. It will be 0.4463. K2 will be 0.1127. Okay, yeah. So with this K1 and a K2, you would have, okay, you would have the desired, basically, time constant and the zeta value right here. Okay, zeta value. Okay, so in the lecture, I do have a simulation there. So I'll just kind of quickly explain this whole thing right here, how it works. Okay, so this is a sort of a simulation here. But I want you to do slightly different ways here. Can you try it out here, okay? First of all, A, B are the continuous system block here, continuous system state space block, okay, matrix. And then I use a C2D here to convert to the discrete, okay? Yeah. So you probably see I didn't have the ZOH at here, right? But C2D's default is zero order whole. So the other way of generating the G and H, okay, is hand calculation and just manually put it into this command line right here, right? Yeah. And then P here is desired pose, like we calculated. Okay, P is the desired pose. Right. The purpose is to calculate the desired feedback gains K. Okay, matrix K. So there are two commands that you can use, okay, in terms of MATLAB. One is called place, the other called Acker here. So basically it's called Ackermann formula that hopefully, yeah, probably we have time to cover, but let's see. Right, there's called Ackermann formula. So there are two ways of calculating the K here. There's a slight difference in terms of these two formulas, okay? So how do you use that is just give the system matrices and then the P vector containing the desired pole location. The MATLAB does the calculation for the K here, right? Yeah. So we spent some time here talking about how, but in terms of a calculation, just one line of code, and then you get the K there, right? Pretty simple, okay? Yeah. And once you get that, and then you can simulate basically with using DLSIM, or even just LSIM is okay. DLSIM, discrete LSIM also works, okay? So here's a response that here. So let's take a look at the response here, right? Let's see. Basically, I want to see the response. If the response more or less conform to our design, right? Remember what our design is. Design is the time constant is 1 second here, right? 1 second. So time seconds. What's the definition time constant? Yeah, time it takes to reach. No. Not steady state.
93.
93? No. 63%. Yeah. Right. So if I look at the response here is a 10, right? But that is not really 10 seconds. This is actually the horizontal should multiply by the sampling time. Sampling time is 0.1 seconds. So basically, this should be 1 second, 2 seconds, 3 seconds, like this. Okay. Yeah. So now if you look at the response here, 63%. So starting from here. Reach down to basically down to 63% somewhere here. So that's pretty close to 1 second here, right? Pretty close to 1 second, okay? And as a matter of fact, you should always have certain error because the design is based on a continuous specification, okay? Continuous specification after discretization, after sampling, you always have certain mismatch there, okay? Certain degrees of mismatch. So that's okay, okay? And in terms of the overshoot, this portion overshoot, and that has something to do with the zeta value, right? The zeta 0.46 right now. If you design a different zeta value, let's say 0.6 or 0.7, and you should expect to have a less overshoot. So in a future lecture, so we'll have another design. Basically, if there is a specification is what's the percentage overshoot you should stick to, right? And that basically will determine the value for zeta, okay? And then will affect r and theta, right? Yeah. Okay. Yeah. So play around with this with this example right here, okay? So that kind of give us a pretty good idea in terms of pole placements, right? In pole placement. But however, if you look at the simulation, you probably will wonder, do I really need to do all the calculations during simulation? You don't, okay? In the simulation, most of the time is you just have to use that place or Ackermann formula to do it, okay? But however, you need to know basically how the MATLAB does the calculation in the background, right? Yeah, in the background. So I think I'll cover the Ackermann's formula today, and then we'll cover another one in the next lecture. Okay. So let's talk about Ackermann's formula. The reason that we use a formula, basically, if you look at the process that we did here, if you think about it, I mean, it's okay if you have a 2 by 2 matrix, right? Let's say if you have a 3 by 3 or 4 by 4, basically the order system increases, and if you still want a hand calculation like this, it's going to take a lot of time, right? And a lot of computations. So that's basically where we need the general formula in here. Okay, yeah. So the general formula of this Ackermann formula is basically, okay, what's our desired? Let's see the desired is z is lambda 1, lambda 2, and up to lambda n. Okay. So once you plug this z equal to this, which means the desired characteristic equation. Desired characteristic equation would be z minus lambda 1, z minus lambda 2, up to z minus lambda n. And if we expand this out, it would take a format of this. Okay, so probably going to take a format like this. Okay, yeah. So that's your desired characteristic equation. Okay, equal to 0. Okay, this is your desired one. If this is a desired one, and what we're designing is we're designing for, right, basically the zi minus g minus hk at here. Okay, so what we want is we want the closed loop characteristic equation to be the same as the desired one here, right? To be the same as the desired one. So we want this guy to be the same as this guy here. So let's say if I call this is alpha cz, if I call this is your desired one here, okay? Yeah. So I need this guy to be the same as this. Okay, I need this guy to be the same as it with a proper k matrix. Yeah. Then the Ackermann formula basically says this. So the Ackermann formula basically saying the k equal this 0, 0, 0, 1. Okay. Yeah. How many zeros? N minus 1 zeros. Okay. So this is 1 by n at here. Multiply by what? Multiply by h, gh, gn minus 1h inverse. Okay. Then multiply by alpha c and g. Alpha cg. So what is alpha cg? See, alpha of z is this guy here. It's this, right? It's this. So alpha cg, basically you replace that z with the G matrix. So the alpha c. So this is Ackermann's formula. Okay, yeah. Yeah, so Ackermann's formula probably hand calculation is still a little bit too much for high order system, but it's okay for computer system. Okay, yeah, for softwares. Yeah. Now I want you to take a look at Ackermann's formula and take a look at the middle matrix that is here. This portion in here. This portion, not a -1 here, just this portion. What's this guy here? Huh? No. What is this matrix? We just talked about it in the last lecture. We had a controllability, we had observability. So when we're checking the controllability, what do we check? We're checking the rank of what? This. This is the controllability matrix, right? This is controllability matrix. So you see, you're taking inverse of this guy here, right? So the premises of being able to take the inverse of this one is because this is which means this has to be inverted, being able to be inverted, and it also means basically the system is controllable. Okay, yeah. So that's where the controllability matrix come into the pictures here. Yeah. Generally, this is for SISO system. Okay. Yeah, for MIMO system, you have the different ones there. Yeah. Any questions? All good? Yeah. So we do have a couple of other options, okay, in terms of calculating the k-edit here. So I think I'm gonna talk about it in the next lecture. And then we'll get on to this reference input, okay? Reference input. Basically, right now it's a regulation problem, right? Regulation, so there's no reference input. So sometimes you don't want to just regulate back to 0. You really want it to control it to a certain reference input, 1 or 2, okay? So then we'll talk about the next lecture. Okay? Any questions? No good?